In this video, you're going to learn how to construct something called mole ratios and then solve mole-to-mole stoichiometry problems. There's a lot of information that is given in a chemical reaction that you may or may not have known. One thing that it tells us is kind of a recipe, and it tells us how much of each reactant we need in order to get to the product or products we're looking for. I've given you a non-chemistry example on your notes page. It says 2 pieces of bread plus 3 pieces of meat plus 1 piece of cheese yields 1 sandwich. This is kind of like our chemical equation that we would have. And the question I ask is, how many pieces of bread would you need to make 50 sandwiches? I think for most of you guys that's a pretty easy question, and you can visualize the problem in your head and figure out that you're going to need 100 pieces of bread in order to make 50 sandwiches. So again, you're going to need 100 pieces of bread in order to make the 100 pieces of bread in order to make those 50 sandwiches. What you may or may not have realized is you've actually constructed an equivalent statement in your head in order to make this conversion of 50 sandwiches and number of pieces of bread. That equivalent statement is that 2 pieces of bread is equal to 3 pieces of meat, which is equal to 1 piece of cheese, which is finally equal to 1 sandwich. And in chemistry, we're going to do something very similar, and then we're going to use that information to actually solve chemical quantity problems. The name that we give to chemical quantities and using chemical equations is called stoichiometry. And a lot of times it'll just be abbreviated as stoich. The dimensional analysis for our problem with the 50 sandwiches would look something like this. Our given was 50 sandwiches, and based on that equivalent statement that I gave you before, we know that 1 sandwich requires or is equivalent to 2 pieces of bread. And so when you solve this, you would take 50 times 2 in order to get our 100 pieces of bread. And like I said, we're going to do something very similar with actual chemical equations and chemical quantities. So I've given you a balanced equation here. Carbon monoxide plus 2 hydrogen gas will combine to make CH3OH, which is called methanol. This is a synthesis reaction, as you might recall, because there is only one product. The coefficients that are in front, in this case a 1's there and a 1 is there, these coefficients can represent 2 different things. First off, they can represent moles. In other words, we could say that 1 mole of carbon monoxide must react with 2 moles of hydrogen gas to produce 1 mole of methanol. The other thing that these coefficients can represent are molecules or atoms or formula units. So molecules, atoms, or formula units. So another way to read this sentence then, or read this reaction, would be 1 molecule of carbon monoxide reacts with 2 molecules of hydrogen to produce 1 molecule of methanol. The thing that you're always going to have to start with in all stoichiometry problems is a balanced equation. That's going to be absolutely critical, that not only is it balanced, but it's balanced correctly. The equivalent statement we can make from this chemical equation, kind of like we could with our non-chemistry example of the sandwiches, would be 1 mole of carbon monoxide is equal to 2 moles of hydrogen, which is equal to 1 mole of methanol. Okay, let's look at this term mole ratio. A mole ratio is just a ratio of any two things in a balanced equation. And when we're talking about mole ratios, we're talking about the coefficients in a balanced equation of the two things that we are comparing. Along with this mole ratio, we know that there are two other conversion factors that we have learned how to do in dimensional analysis. The first one was going from moles of something to things like atoms, molecules, and formula units, and back. And if you remember, whenever we're using this conversion factor, we always put a 1 next to mole, and we always put Avogadro's number next to the word atom, molecule, or formula unit. The second one that we learned in the last chapter, chapter 6, was going from moles of something, and A is generic for something, to the mass, in other words, the grams of that same exact thing, and back. And remember, number 2 we called molar mass. And whenever we used molar mass, we always put a 1 next to the moles, and we always put the actual molar mass number next to the grams in the conversion factor. And now this third one is the only one where we can actually convert from one thing to something totally different. So we can go from moles of A now to moles of something totally different, or B, and back. And this is called the mole ratio. And in the mole ratio, we're going to put the coefficient of A next to that part, and we're going to put the coefficient of B next to that part. So the question I gave you there was if we want to know how many moles of CO are needed to produce 2.3 moles of methanol, what does the visual setup for the problem look like? Typically, what I try to do is visually set up the problem, and what that means is write out the balanced equation. So 1 carbon monoxide plus 2 hydrogen gas yields 1 methanol. And what I mean by visually set up the problem is underneath each thing, write down what we have. We know that we want 2.3 moles of methanol, and we're being asked how many moles of carbon monoxide. So under carbon monoxide, I'm going to put question mark moles, so I know that's what I'm looking for. That's the visual setup for the problem. Now let's go ahead and try to solve this problem using those 3 conversion factors that we just talked about. We're going to start out with the given. In this case, it's 2.3 moles of methanol. So moles of methanol is going to go here. And one thing that's going to help us is now we're allowed to go from moles of one thing to moles of something totally different. So let's go ahead and do that. let's go to moles of carbon monoxide. And it's this thing here, moles over moles, that's called the mole ratio. Going from moles of one thing to moles of something totally different. And remember, what we're going to do is use the balanced equation. So in front of moles of carbon monoxide is going to go the coefficient for carbon monoxide. And in front of moles of methanol is going to go the coefficient for methanol. So that's what our dimensional analysis is going to look like. So this is going to be 2.3 moles of carbon monoxide. So there's our final answer, 2.3 moles of carbon monoxide, because the moles of methanol cancels out. And again, it's this thing right here that's called the mole ratio, moles over moles. Okay, here's practice problem A. It says how many moles of oxygen gas will be produced from the decomposition of 5.8 moles of water. The first thing, remember, that we need is a balanced equation. So we know that water is decomposing, and we know that that should decompose into hydrogen and oxygen gases. There's our equation, but it's not balanced yet, so we need to balance it. And the balance of this is going to look like this. Now let's visually set up the problem. We have 5.8 moles of water, so under water I'm going to write 5.8 moles. And it says how many moles of oxygen will be produced. So under oxygen I'm going to write question mark moles. Okay, let's start out with a given, 5.8 moles of water. In our dimensional analysis, remember that whatever unit is here always is the unit that goes down here. So that means the unit down here is moles of water. And we know we can go directly from mole to mole, so let's go ahead and do that. We're going to put mole on top, but on the top we're going to put moles of oxygen. So here is going to be the use of our mole ratio, and that's going from the moles of water to the moles of oxygen. Remember, in order to fill in the numbers here, we need to use the balanced equation. So the number going in front of water is going to be the coefficient of water. The number going in front of oxygen is going to be the coefficient of oxygen. Let's go ahead and put those in now. The coefficient of oxygen was 1. The coefficient of water was 2. So this is what our dimensional analysis is going to look like. So essentially 5.8 divided by 2, which is 2.9 moles of oxygen. So there's our final answer for problem A. Okay, in problem B it says ammonia is produced by the combining of nitrogen and hydrogen gases. Calculate the number of moles of ammonia that can be produced from 1.30 moles of hydrogen. Let's first come up with a balanced chemical equation for this. We know that we're producing ammonia, and produced is a sign that that's on the right side of the reaction, and it says it's produced from nitrogen, which is N2, and hydrogen gases. So there's our unbalanced equation, and then balanced will look like this. So there's our balanced equation that we have to start with in order to do our stoichiometry. And we're trying to calculate the number of moles of ammonia. So under ammonia I'm going to put question mark moles. And we're starting with 1.30 moles of hydrogen. So under hydrogen I'm going to write 1.30 moles. Now let's go ahead and start with the only number that we were given in the problem, which is 1.30 moles of hydrogen. So down here we're going to put moles of hydrogen, and on the top we're going to put mole of ammonia. And remember, mole over mole, this is our mole ratio, and we're going to use the coefficients in the balanced equation. So the coefficient of ammonia is 2, which means we're going to put a 2 right here. And the coefficient for hydrogen is 3. So we're going to put a 3 on the bottom. When I put this in my calculator, I get 0.8666666667. And here we're going to need to utilize our sig figs, which is 3 sig figs from 1.30. So my final answer here is going to be 0.867. That's 3 sig figs, and our unit is moles of ammonia. So there's our final answer for B. Okay, practice problem C says, how much nitrogen will be required if I want to react 2.9 moles of hydrogen to make ammonia? So it looks like we're using the same balanced equation as before. So nitrogen gas plus hydrogen gas going to ammonia, and we do need to balance it. There's our balanced equation. It says how much nitrogen. So we're looking for the moles of nitrogen, and we have 2.9 moles of hydrogen. So let's start out with the only number that we have here, which is 2.9 moles of hydrogen. Now on the bottom here is going to be moles of hydrogen. Again, whatever unit is right here is always the unit that goes at the bottom there. And on the top we're going to put moles of nitrogen, and we know that we're allowed to go from mole to mole, and we call that the mole ratio, and we're just going to use the coefficients of the balanced equation. So the coefficient of nitrogen is 1, the coefficient of hydrogen is 3. So that's what our dimensional analysis is going to look like. And we're going to need 2 sig figs because of this in our answer. So 2.9 times 1 divided by 3, that's 0.9666666, repeating with 2 sig figs. That's going to be 0.97 moles of nitrogen.